Okay, so shall we start? I think we have a forum. So okay, so we have come to the last leg of the course, 9, 10, 11, 12. 9 we saw before quiz 2, week 9. So that was about perceptrons, and we'll start from where perceptrons ended. Right? So that is where we start. We look at support vector machines in this week and also in the next week. And finally, we'll wrap it up with some bit of neural networks in week 12 and a unifying perspective about all the classifying techniques. So Sir will discuss that. Okay, so is there anyone who has not watched the week 10 videos? I think there was like 1 week. So I am hoping all of you have watched the videos. Anyone who has not watched?
Sorry, I didn't actually, not complete.
Okay.
I got stuck at the third one. I could not make sense of it, and
All right. Okay.
I
Getting
stopped.
stuck is fine, but at least you have at least watched a couple of them, right? So
Yes, I did. That I did.
okay, sure. Okay, that's all right. So I'll go. It will be more of a summary, but it will be fairly detailed, but not too detailed. So I may skip the proofs. Not
Okay.
right.
Sure.
Right. So we'll start now. Now what we have is this is what we'll be doing in today's session. We'll go through what this concept of margin means in little more detail, and then we look at the concept of max margin classifier. Right? SVM is actually a form of what is called a max margin classifier. We'll look at why it is called that way. Third thing we'll do is we'll look at duality very briefly. Okay, because most of you have either done it in MLF in the last term, or I'm sure you would have gone through the week 10 videos in MLF, which would have talked about duality in extreme detail. Right? So I'm sure you would have just gone through that this week. So I won't be going into it again. I'll just use whatever is required for SVMs and stop it at that. The fourth thing is we look at the weight vector in SVMs and understand geometrically what they mean and how this duality helps us find this weight vector. And then we look at what support vectors are, right? Why is it called a support vector? What is a support vector? All that. And we'll finally wrap it up with the overall picture of hard margin linear SVMs, and briefly we look at soft margin SVM, right? So that is what we'll do. While discussing soft margin SVM, I pull in some concepts from week 12, okay, because they are connected to SVM, some concepts. So that will, while you are watching week 12 lectures, it will also be useful, right? So that's the outline. So we start from where perceptrons ended, right? So perceptron will be our starting point. So we looked at linearly separable data with gamma margin, right? That is the fundamental assumption that we started off with while building perceptrons is that the data is linearly separable, not just any linearly separable data, but some gamma margin was there. And we didn't actually go into detail of what this margin actually is. All that we wanted in perceptrons was that some margin should be there. So that is all we wanted. But once that requirement is there, once some gamma margin is satisfied, we could actually come up with infinite number of classifiers, right? So for example, if you have this data set here, you can draw one valid classifier like this, another one like this, right? And anything in between these three configurations, right? So all these are valid classifiers, and unfortunately or fortunately, depending on how you want to look at it, you have too many of them, right? So that is the first point. So perceptron, what it does is it gives you one valid linear classifier, right? It could be any one of these three. There is nothing special about the classifier it returns. All that perceptron tells us is that if you give me a linearly separable data with gamma margin, I will give you one of these lines, right? It doesn't make anything. It doesn't state anything more than that. Okay, so that is perceptrons. But naturally, the question then arises, right? So, if there are so many options available, is there a way I can choose the best option, right? Is there a way I can pick up the best classifier from the slot? So, whenever you ask such a question in mathematics or in mathematically oriented disciplines, you are bringing in some notion of best, and you have to define what this best is, right? So, the next question from here is, what do you mean by best? Okay, so this is what we'll be looking at in the next few minutes. What do we mean by a best classifier, or how do we even think about this?
If there is no misclassification,
Uh, yeah, but there are so many classifiers, right? As we all these three, for example, there are three classifiers here. You're right. That is one notion of best, right? That's a good point. That is one way of defining best. That which gives you zero misclassification on your say training data set. This is one notion of a good classifier, right? But as we have just seen, that is not sufficient. Why? Because, well, okay, that's a good working hypothesis, but the question is, can we come up with a better definition of best? Okay, that is what we are going to look at, and that will take us to the idea of the margin, right? So if you look at this data set here, this is some linearly separable data set with some gamma margin, right? Now, what do you what is bad about this particular configuration, or is there anything that is bad about this?
There is one point in the decision boundary.
Okay, so this if you are meaning this black one, this that's the origin, right? So
Okay, okay.
right, yeah. But other than
Yeah.
that, what
If you have to revise the boundary based on new additional data, this may not work after that.
right, that's the main point. That's the most important point. So assume that you have additional data, as you just mentioned. I'm calling them. So these are four new data points, right? Now these ideally they are coming from the test set, right? So assume that they are coming from the test set. Now, what do you expect these 2 points to be to have as the true label, right? What do you think will be the true label of these two white points?
Sir, what did you say about that black dot, sir? That black
That's
dot?
the origin.
That's the origin. Okay. Yeah. Yeah. So regarding these 4 points, I think the point on the left hand side will go to -1 and the right hand side will go to +1.
So before you classify it using the this particular classifier, in terms of by
They
looking at
belong
the
to the right
data,
side of the boundary.
sorry,
They belong to the right side of the boundary.
yeah,
No,
if you were to give a
two on the
label
left
to,
side, two on the left side, and two on the right side. I think.
okay, no, yeah, that's correct. But I'm asking more in terms of if you were to guess the true label of these two white points, will they be green or red? What is
The
more
top,
like?
the top two will be red
So
and the
green.
bottom two will be green.
No, don't
Uh,
look at the prediction.
visu- Visually, if I had to say, they'll all be green.
Okay, these two will be green, but do you think these two will also be green?
No.
More likely to be red.
Yeah.
Yeah.
So, yeah. So the point is, I'm asking you from the data distribution, right? I'm not asking you from the point of
Right.
you have got this classifier,
Yeah.
right?
Yeah.
So
Yeah. Yeah.
you expect the data to be these 2 points to have green label, true label, right? And you expect these 2 points to have red labels, right?
Yeah.
Why,
And
sir?
Yeah.
Why, sir? They are on the right side. The
no, no,
bottom points
I'm
on the right
yeah,
side
that's
of the
correct.
classifier. Yeah.
We are not asking about the prediction, right? So prediction is going to be wrong as you are pointing out, but what is the likely chance? How likely is it that these 2 points come from the green class, right? The true label. They belong to the true side, right? So this right hand side belongs to the green and the left hand side belongs to the red, right? So there is more chance that the true label of these 2 points are green.
No, just a small clarification. So it's not about whether my answer is getting right or wrong. That's of secondary importance. The line with the dotted dot which you are calling origin, right? Hello.
Origin, the
The the,
black
bl-
point is
the,
the
the
origin.
the black point is the origin. So the line which is passing through the origin, we are calling it as a classifier, right?
Correct, yeah.
We are calling it as a classifier. If I am getting four data points or four new data sets, and two of them are on the left side of that origin, then how can I call them green?
No. The point, the question, the point is, GP. Let's assume that line was not there. Those lines were not there at all. Just looking at the data, what would you say it is likely to be?
Then I can say everything green, everything red.
No.
No,
How
you have
likely
one
is
cluster of data on that side, one cluster of data on this side, no GP.
Yeah, these two green, these
Okay,
two
if we
G
are
on the
going by
top.
cluster wise, yeah, then
Yeah,
those
yeah,
are
Yeah.
those seem to be green and
Yeah.
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 Yeah, right. So more likely to be green, more likely to be red. Right? Actually, we don't know because they are from the test set, and we don't know exactly what class they could belong to. But probabilistically speaking, they are more likely to be green and red. Right. So the point is, this particular classifier here is doing a bad job, right, on these new data points because it's going to predict them as red, red, and green, green, assuming that the actual true labels are GGRR. It's going to give a wrong prediction on these 4 data points, right? So the outcome of this picture, what we need to understand is that small margins do not generalize well, right? So what we mean by generalize is that they don't perform well on unseen data, right? So that's ultimately what we want a classifier to do, right? It needs to perform well on data points that it has not seen before. Now, because of this very narrow margin, there is a higher chance of making mistakes, right, on unseen data points. So for the same data set, we have a much wider margin available. In fact, in some sense, this is the best margin. This is the largest margin that you can think of. And notice how for this classifier, the outcome is perfect, right? In fact, it classifies the green points correctly, the 2 red points correctly, right? So larger margins generalize better. Okay, so is there any confusion in this particular?
You said this you have drawn.
Hello? Yeah.
GP, you're on mute.
Yeah, some background noise came, so you know. Sorry, yes, I'm trying to say, sir, that on the right hand side, the figure you have purposefully drawn like that. Like you know, now those points have been shifted towards the margin dotted line, right?
Those points,
The
which
third,
point?
the third diagram. Let us talk about the second diagram, the third diagram. In the second diagram, all the newly added 4 points were very close to the axis, right?
Very close.
The
No,
four
right? They're
white.
very far away from the.
No. I'm saying that in the second diagram, all the newly added 4 points are very close to the axis, right?
Correct. Yeah, yeah.
In the third diagram, purposefully you have drawn like that. That now those points have been shifted from the margin line also. I'm dotted line. I'm calling it as a margin line, right? That gamma part I'm calling it as a margin line, right? So the new classifier which we are getting out, purposefully we have shifted towards that. Say for example, if those points are still in between the solid line and the dotted line, then how I will classify it?
The margin has nothing to do with the final prediction. So if the point falls
So
between.
what are these dotted lines in the what are these dotted lines? Dotted line are related to margins only, no, sir?
Correct, but that is not going to influence your prediction. The supporting hyperplanes, as they are called, these are the technical term for them is supporting hyperplanes. They
Yeah.
are useful while training your model. Once you have trained the model, and when you are predicting, you're using your model to predict the
But
margin. The supporting hyperplanes are no longer interesting, right?
but these supporting hyperplanes are dependent on gamma only, no, sir, on the value of gamma.
So
How?
I won't say dependent. Gamma is linked to each. For every weight vector, there is a gamma associated with it.
Okay, so let us ask if, those 4 dotted points, two on the red hand side, if it is in between the solid line and the dotted line, then how will I classify?
Here in this case,
Yeah, in the third diagram, yeah, these two white points, if they are in between solid line and the dotted line, then how will I classify?
just like you will use any. So this is ultimately SVM is a linear classifier, right? Anything that falls on one side of the solid line is green. Anything that falls on the other side is red. So that's what I'm saying. You should not confuse the supporting hyperplanes with the prediction part of SVM, right?
Anyhow, sir, I will come back to this question again once you get into the formula because I am confused. Like W transpose X multiplied by Y, right?
Yeah.
My professor is saying that multiplied by Y should be greater than equal to gamma, and this line is an indication of gamma only. So if point is in between that, then what classification I will do? So maybe once you get into the formula part, then again I will come back into this
Okay. Yeah.
question.
Okay. Others, I think we can move on. If there are questions, you can let me know, right? See, the point of SVM is we are looking for classifiers which have maximum margin, right? So now I hope this part is clear. Why we prefer large margins, right? If it's not, let me know. I will come back to this. So now the entire question now depends on the idea of margin, and we have to make this idea more precise, right? So for any classifier, every classifier is associated with a weight vector W, right? So W transpose X equal to 0, that's the question boundary, and every classifier is associated with a particular weight vector W. And what you have to do to find the margin is you'll have to look at the point closest to this classifier. Okay, so if your data is linearly separable with some margin, right, some non-zero margin, you will always find this point. Do you all agree with that statement? If you have a linearly separable data set with some margin, whatever be that, so margin here is what? The distance between the classifier and this point, right? So you'll always be able to find the closest point. Does everyone agree with that statement? I hope you do. So once you do that, what happens is that you can scale your W such that X star lies on W transpose X equal to 1.
Sir, could you please explain that a bit geometrically, the scaling and the scaling part of it?
Okay, yeah. So I'll there is a separate slide I have. There's a separate place I have for that. So let me probably take that up. Are you able to see the screen?
Yes, sir.
It's the same diagram. So instead of X star, I'm just calling this X. Right. So there is this may be a bit easier to relate. So X is on some line W transpose X equal to gamma. Right. Let me write that down. So this is the line W transpose X equal to gamma. Okay. Now you don't know what gamma is, right? Well, let's say you have not, you call this gamma, and the closest point is having gamma margin from W. That's what we assume to start with. So let me also write down what this line is. This is W transpose X equal to 0, your decision boundary, and this is W transpose X equal to gamma, and we say that the data set is having gamma margin because of this. Are you clear so far?
Yes, sir.
Okay,
Yeah.
now what you do is remember what we did in PCA, right? PCA, we did the same thing. What we did was we tried to find the projection of X on W, right? We'll do the same thing here. So if you want to find the point XP, XP is nothing but this projection of X onto the weight vector. It's nothing but X transpose W by norm W. Okay, so if you remember in
Just a bit going back, what is XP? The projection of X onto the W.
yeah, it's the projection of X onto W as this point.
Right, sir.
Okay, so if you remember in PCA, we wrote the projection vector as
X transpose W by norm. Right, sir.
right. So in fact, we would have written this as X transpose W W because norm W is 1. Okay, so
Yes, sir.
now if norm W is not 1, you have to divide by norm W square and all that. But eventually, you'll end up with this formula: X transpose W by norm W. Okay, so
Right, sir.
another way to understand is that if you do the dot product, it's norm of X, norm of W into the cosine of the angle between them, and you can think about this as norm of X cos theta, right? That is nothing but this particular projection.
Right, sir.
Okay, so the distance between a point, the perpendicular distance of a point from a line with defined by W is X transpose W by norm W. That is the okay. Now what we are doing is this is the gamma part that we are doing, right? Now X transpose W is what for this particular point? The point lies on the line, X lies on the line, W transpose X equal to gamma, right? So what will be the value of X transpose W?
Gamma.
It will be gamma, right? So I can replace, so I'll just write this down. I can say that D is equal to gamma by norm W. Can I say that? Distance
Yes, sir.
between these two lines is gamma by norm W. Now, what I'm doing is I'm going to scale W in the following way. So I'm going to say divide both these sides by gamma. That's not going to change anything. So I'm going to say will take time, but it's okay. So I'm going to say that divide both sides by gamma. Now, will that change my decision boundary? Will that affect my decision boundary if I divide both sides by gamma?
No.
No, right? In fact, this was a quiz question. If you multiply quiz 2, if you remember, if you multiply, if you have W and you have 3W, how many points will be misclassified? That was one of the quiz questions, right? That will be the same because you have not changed the decision boundary. So if I divide W by gamma and I do the same here, what do I end up with? So let me write
1.
this.
So you'll end up with 1.
Right, I'll end up with 1, and I'm doing this. I'm doing something similar here, right? So now X transpose W. Now this is where it gets a bit confusing. Let's call this a new W dash, right? So I can in fact write this down as 1 by norm W dash. Do you agree to that?
Right, so
Okay, so now here in this slide, what we are doing is we are doing all these operations at one go, and we are just saying that distance of X star from this line is 1 by norm W. It's actually gamma by norm W, but you're scaling W by dividing it by gamma on both sides, and you should actually use a new variable name called W dash. But just to get along with this particular W and not use something else, we are just calling it W itself. Actually, it should have been 1 by norm W dash, but we are replacing that W dash with W because it doesn't make too much of a difference.
If it is okay, may I request you to repeat the last 5 minutes when you started with how you are actually getting D is equal to gamma by W, norm W?
Yeah, sure. So you have
the below one, the projection part is clear.
okay.
That part is clear. But my question stems from normally when you have two lines which are parallel, W transpose X is equal to 0 and W transpose X is equal to gamma. I always assume that the distance between the two lines is gamma.
Okay.
Because it's the offset of the line itself is.
Yeah, that's gamma only if norm W is equal to 1.
Okay.
Okay, if it is not equal to 1, so we tend to call it gamma. It's correct. So what we are doing is we are not scaling it. That's all. So your intuition is right. That this. So let me go back to this being W transpose X equal to gamma itself. So you are right in saying that this line and this line have a distance of gamma. Only thing is that you are using a different set of units. It's like saying, let's say you are measuring gamma in kilometers, and then you are scaling it by 1 by 1000. So you are now measuring it in some other unit, say meters.
Okay.
Right. So I don't know if it's multiply or divide, but some scaling, right? So you are still correct in calling the distance between these two lines gamma. Only thing is that you are using different set of units.
Okay. So
you had initially got some relation between D and gamma that you changed. Can you go back? Like the image has changed.
Yeah. So I'll just do this one step. I also went a bit fast here. So let's start with where we were. No? We were here, and let me remove this cos theta business. So this is what Just gamma by norm W, right? This is, you agree till this part?
Yeah.
Okay, now
No,
what we are,
this was my confusion actually. Yeah.
okay. So this is fine now, or
Yeah, it's fine now.
okay? Now what I'm doing is I'm going to rename things. I'm going to call this. What shall I call it? Call it W prime. Okay, by just scaling it, I am not losing anything. So let's also explicitly mention what W prime is. W prime is equal to W by gamma, right? So this is the new W. I'm calling it W prime. So by making this transition, what happens? W transpose X becomes uh, W dash transpose X equal to 0. It doesn't change anything. The line remains the same.
Yep.
Now, what happens to this expression of the line, right? So this will become, if you divide both sides by gamma, what do you get? 1 by gamma W transpose is equal to 1.
Yeah.
Now the next step will be, I'll use this to call this W dash,
Transpose.
right? W prime transpose. I'll call it this. So now,
Yeah.
so this is what I have done. Now, see, W by gamma is W prime, right? So let's do that here. So I'll divide both numerator and denominator by gamma. So I'll end up with W by gamma, right? Now I can further represent this as 1 by W prime. That you agree? This is the sequence of steps that we have done.
Yeah.
Okay, now all that we are doing is in the lectures, we are calling this W instead of W prime, and we have not changed anything. It's just we're going back to naming W prime as W. It doesn't change anything.
Yeah.
Sir, a couple of quick points, sir.
Yeah.
So W transpose X equal to gamma, and even X transpose W equal to gamma, both are same here, huh?
Yeah, both are
W transpose X and X transpose W, right?
right. Right. Yeah, both
And,
are.
and what Ravi was asking, in fact, I think that's the doubt of most of us. Like when we are saying that, once again I'm coming to the line passing through the origin, that W transpose X equal to 0, right?
Yeah.
And when I am multiplying my point W transpose X multiplied by Y, and I am getting a gamma, right? So isn't this gamma is the distance of the line from the origin?
Yes,
Isn't it?
it is the distance, but if you are very strict about talking about distances, then gamma is not the distance, but gamma by norm W is the distance.
But margin means that only, na sir. Like
No.
how since week 10 is highly related to week 9, you must agree to this, right?
Right.
In week 9 perceptron, when sir was discussing, then he took a case where he intentionally took 3 points on the x-axis and y-axis, right?
Right.
And then he did some manipulation, and then he shown to us that, see, my perceptron is not converging here, right?
Correct.
So then he led us to that, now we need to put some margin. From there the concept of margin has come, if I recollect correctly, right?
Ganga
Correct.
Prasad, may I try?
Yeah, yeah.
May I
Now
try?
let me complete my question.
Yeah,
So
sure, sure.
from there the question of margin, the concept of margin has emerged, right, sir?
You are asking from where or from there? You're
No, no,
saying.
I'm saying from there itself. He took an example
Yeah, yeah.
by taking certain points on axis itself, and
Correct.
when we did multiple trials, like
Yeah.
W transpose T plus 1 equal to W transpose W T plus X into Y, my perceptron was not converging,
Yeah.
right? I was not
Correct.
able to predict correctly, even after
Right.
multiple trials. Then he said, now we have to introduce the concept of margin. From there, the concept of margin came, and till now, the understanding has been that gamma is the distance from the origin. We are giving some margin. So
Correct. So yeah,
why is
you're
not the
correct.
distance? Why is it not the
No,
distance
I,
from
I
the?
never said it is not so what I'm saying is it's not exactly the distance. So for example, there are actually, if you look at the literature, there are two concepts of margin, right? So there is what is called the algebraic margin, and there is what is called the geometric margin, right? So if you have two lines, say W transpose X equal to 0 and W transpose X equal to gamma, then the algebraic margin is gamma. Okay. That's what we use in the gamma margin. Now, what is the geometric margin? It's this, right? And what I'm saying is this is the distance. You can of course talk about the previous one also as the distance. You are correct. But only thing is that I will probably use a different unit, right? So if to make it simple, if
Let us take very layman example. From my origin, my dotted line is at a distance of 2 centimeter on the right hand side, and on the left hand side also it is at a distance of 2 centimeter. So what will I call this 2 centimeter? Will I call this 2 centimeter as gamma, or will I call something extra?
Ganga
you
Prasad, may,
Yeah,
may
yeah,
I,
Ravi.
may
Sorry,
yeah,
you
go
were
on.
saying something.
okay.
You were
Go on.
saying something. Yes, yes.
Let's leave this transpose and all these matrices and all that
Hmm.
aside. Just go to
Yeah.
a regular graph.
That's why I give that example. Na?
Yeah,
If I am
x
at
is
a
equal to
distance of
2. So
if I am
let's
at a
take the
distance of
example
2
of
centimeter,
yeah, example of line which is vertical. X is equal to 2, x is equal to 4.
hmm,
Distance between 2 is 4
2
minus 4.
unit.
Done.
Yeah,
Okay.
2 unit. Yeah.
Now if it is ax is equal to 2 and ax is equal to 4, then what is the distance?
Yeah, but
It is
here it is.
x
But
by
here,
2
here
by
the
a and 4 by a.
I got your point, Ravi. But here, where that A is coming, because W transpose X we are taking as zero, na? So that is becoming my origin. And from
W transpose is the vector, right?
W transpose X, yes. So we are doing the dot because W transpose, yes, that's what I'm saying. W transpose X, X is also a vector. W transpose X is also W transpose is also a vector, and it's a
Correct.
dot product. So we are getting zero over here, and that is my origin.
Uh, you're right. W transpose is a direction vector, correct?
Yes.
If you take it as a direction vector, it can be unitary or it could be anything.
No, here we are getting zero because the classifier and the directional vector are perpendicular to each other. That's the reason why we are getting zero.
Correct. If we take the direction vector as 1, 0, and minus 1, regardless of what uh, let's say x is some set of fixed values, 2, 0, and 2, 3, and 2. W is 1, 0, and minus 1. Even if W is 2, 0, and minus 2, it still will satisfy, correct? You're getting what I'm saying, right?
Hmm. Yes,
So
yes.
if you say unit norm, that is a little different.
So you are saying that gamma is a distance, and geometrically, what Ravi was saying that let us take ax equal to 2, and then x we will.
W is a weight factor, right? It's a weight
Hmm.
vector. So weight can be proportionally, you can increase or reduce.
yeah. So if you want to be absolutely sure of calling it a distance, then I would. This is the distance, right? This is geometry, right? You can't change geometry. You can't say that this is d is gamma, right? So d is well gamma by norm w. If you want to exactly call it distance, then it's gamma by norm w. But at the end of the day, as norm w is just some say scalar, right? So you can just scale it and say that's also distance,
Yes.
right? So
Okay.
it's
Let us
okay.
proceed.
You are correct in calling it a distance. All that I'm saying is, if you want to be a very correct about what you're saying, gamma by norm w is the geometric margin, gamma is the algebraic margin.
Okay, sir. Let us proceed.
Okay, so is there any other question on how we arrived at this notion of the distance?
Can you go back to the picture you were showing again,
Okay,
please? So here the D is gamma by norm W. I understood that, and how you can like gamma is what in that geometry part?
here,
Yeah, yeah, yeah. In that part, uh, mm, I understood that D is there. I can see it. Okay, but where is gamma? Like which distance are you calling the gamma?
it's a scaled version of d, right? It's a scaled version. If you multiply, so if you multiply this d by norm w, you will get gamma, right? So see, d is what I'm saying. D is gamma by norm w.
Mm-hmm.
So if you want to understand gamma geometrically, it's nothing but it's a change of, think of it as a change of units, right? I can either call the distance between this as 1 kilometer, or I could call it 1,000 meters, right? I'm at the end of the day, distance is distance. Only thing is that I'm using different units to call them, right? So whatever you all understand as distance is correct, right? You can think about gamma as the distance. It's not wrong.
Yeah, but gamma is the distance from where to where?
Of this
That's my
point from the decision boundary.
okay. From this point x to the distance boundary.
Yeah,
Solid line and the dotted line.
yeah.
Solid and dotted line.
Okay.
Okay, so sir, the overall distance between the negative margin and the positive margin would be twice of gamma, right?
Yes, yes.
All right, cool.
Okay, so to be more specific, it will be 2 by norm W, right? In this case, since we have eliminated gamma or made
Right,
gamma
sir. Right,
1,
sir. Right, sir.
okay, so let's now continue. So this is the margin, right? So the proper definition of a margin is the distance of the closest point in your data set from your linear classifier, right? So this is your classifier. This is the closest point, and every data set will have this point, right? You can always find this point, and this is the margin. Okay, so once you have defined what the margin is, the constraints of the problem tell you that all the points in your data set should lie outside or beyond this margin, right? So again, this margin is kind of used interchangeably with these dotted lines, right? So you have to know what we are talking from the context. Okay, so is this part clear to everyone how we ended up with this inequality?
Sir, I was asking this doubt only at the beginning. Then I said once you get into the formula, then I will come back again. So now here what we are saying, say for example, margin is 1, right? And that's the reason why we are saying W transpose X multiplied by YI. If it is greater than equal to 1, I will classify it as plus 1, right?
Yeah, the algebraic margin is 1. Yeah.
The algebraic margin is 1, so it is so even a point is on the dotted line, I will classify it as plus 1 means green. And if it is on the left hand side on -1, then I will classify it red. I am asking if it is in between the solid line and the dotted line, then what will I do?
The first point is what I don't agree with, right? So you will classify it as green, not because it's on the dotted line or it's beyond it. Anything to the right of your decision boundary will be green. Anything to its left will be red.
Okay.
Okay. Now this you have to you have to separate the testing part in SVMs from the training part, right? For training of hard margin SVMs, especially in the linearly separable case, right? No point will lie between the margins. That's an assumption, right? We are just like we had the linear separability with gamma margin assumption.
For the training part, na?
For the training part, no point will fall between these two dotted lines.
Correct. That's how we are training our model by bringing gamma into consideration, right?
Correct, correct.
That's the training part. But what about test part? If a point falls in between solid line and dotted line,
No,
so
in the testing phase, right? The dotted line doesn't matter at all to you. You have a
okay.
linear classifier with you, right? So how did you do?
Okay, so you are saying in that case I have to consider the solid line as my classifier. Anything on the right hand side of the classifier will be green,
Correct,
and on the left hand side it will be red.
correct, yeah.
Okay, so in testing part you are saying gamma is not playing any role.
Yeah, once you find W, that all that you need is W, right? And you have to find the sign of W transpose X for classify. That's all.
But then what is the significance of this formula W transpose Xi Yi greater than equal to 1? Then only I will call it as plus 1.
No, we are not saying that then only you will qualify. We'll call it as class 1, right? What this formula is saying is that every green data point lies either on the line W transpose X equal to 1 or it lie away from that. That's what this is saying.
For the training part.
For the training data points, yeah.
Okay, fair enough. Fair enough.
Okay, I have one other question here. W transpose Xi is supposed to lead up to the projection of the actual Y onto the space on which these points are, correct?
Actual X onto W, right?
No, W transpose X itself. If I say W transpose X, the weight vectors multiplied by the data points will lead me to the projection of Y on the plane on which the data points are, correct? In case the Y is outside the plane.
Oh, you're talking about it from the linear regression sense, is it?
Yeah.
Not. See, the best way to understand W transpose X is as a distance, right? It's measuring is how far away from the classifier is your point X. It's the projection of, W transpose Xi for this green data point will be how far away this green point is from the solid line.
Okay.
Okay, it just let us. It may not be appropriate to think about it as projecting it onto the space of the data
Okay.
points.
Okay.
Okay, so did everyone get this part? Why it is greater than or equal to 1?
I think that is where I would like some more.
Okay, so
explanation.
I will go to the last set of slides and I'll revisit them. May not be appropriate, but since you have this, so see, the pretty soft margin, but I have the image here. So this is same setup. This is W transpose. Okay, forget this. This is wrong. Actually, okay, this is wrong. So this is W transpose X is 0. This is W transpose X is equal to 1.
Okay.
Okay, this is a point that lies on the green line. Okay, now forget about all these things. We don't need them. Now I'm going to draw another green point, but this time this green point is on the line W transpose X is equal to 1.5.
Right.
Okay, now what we have to, the way we have to understand this is that the green data point is at a distance of 1.5 units from my solid line. Of course, distance, scale distance, right?
Right.
This is at a distance of 1. Now, if you look at something that lies on the decision boundary, it is at a distance of 0. Okay, if you look at a point that is here, it's at a distance of
minus 0.5.
Yeah, right, minus 0.5. So that is all W transpose X is telling you. Now,
okay.
Right, now, do you see why W transpose X into Y should be greater than or equal to 1? Everything should lie beyond this margin.
Yeah. Less than would come within the boundary. Okay.
Yeah, less than will come within the
boundary. When I say the dotted lines, lines is where it will come.
Exactly.
Okay, got it.
Is there anyone else who has a question about this? Not really.
Thank you.
Okay, right. So see, for the red points, what will happen is that W transpose X will be negative. Okay, W transpose X will be negative, but because YA is minus 1, you will end up with the whole expression being positive. That's why what we should do is we should probably write a separate set of equations for the red points and the green points. But because of this nice trick of multiplying it by the label, we are able to write a compact expression like this. Okay, so now what is our goal? Our goal is to maximize this margin. Okay, the margin is what? 1 by norm W. Recall that's what we arrived at. And we have to maximize this margin subject to these constraints. There are n constraints, one for each data point. So this is our optimization problem. So how do we recast this? Is there a different way of writing this? Can change this into a minimization problem with just taking the reciprocal and squaring it, right? So we end up with this problem.
Could you come back again, sir? Like from where this half factor is coming, sir? 1 by 2. Yeah, here there is no half factor, but yeah.
Okay, so ideally we should have written it as 2 by norm W, but it's okay, right? So 1 by norm W is the margin. Now, for mathematical convenience, you can bring in this 2. As far as the optimization problem is concerned, it doesn't change anything. But when you differentiate norm W square, you will get a 2 and then that will cancel out. So you can think about it that way. Or alternatively, the actual width is what? 2 by norm W, right? This distance is, if D is 1 by norm W, the width of this, the width between these two dotted lines is 2 by norm W. Is that fine?
That half factor has come, sir. What we had discussed, I think last week, that for the sake of convenience, when we take the loss part, so in regression, many people take half.
Correct.
It is the same logic, right?
Yes. You could think of it that way, or if you want a more geometric way of looking at it, the distance between these two dotted lines is 2 by norm W. So you could say then 2 came in.
Because in this course, our professor Arun Kumar had never taken that factor half, but for the first time in week 10, he has taken that factor half.
Right. Because he's talking about the width of this.
Okay, let us proceed.
Any other questions? Because this is like one stage of the session, right? This is what we call a max margin classifier, right? So we are trying to maximize the margin subject to some constraints.
Sir, which one is correct? So we have one equation where our aim is to maximize over W, and another equation where the aim is to minimize over W. Both of them will yield the same optimal answer, or is there some difference?
They are the same, right? Because if you want to maximize this expression, what should you do? You should make norm W as small as possible, right?
Right, sir. And then in the other expression, we're minimizing norm W the whole square, and
Yeah.
then we're
So
taking half of it. Right, sir. Got it.
okay, so we are doing the same thing, so they are equivalent. Any other questions?
Right, sir. Got it.
Okay, so we'll move on. So see, this is, I'll just go over this quickly because this is more of the mathy aspect of it, and you can always go back and watch week 10 of MLF. Okay, same thing has been done in great detail. So I've just taken a general problem, right? You have to minimize f of w. Here f of w is this thing, okay, subject to some constraint, some inequality constraint. And if you recall, you can write this as.
Sir, can you please
I
put
think we should
Vasu
mute
on mute, sir?
Vasu something.
Yeah, somebody's snoring actually.
Vasu might be snoring.
Maybe he's just tired. Who knows? It's perhaps a long day for him.
Yeah, I think some of them have DBMS OPT tomorrow. I think they should be. Anyway, right? So this is. I hope you all agree that you can write this expression, this equation, sorry, this problem like this.
Lagrange came into picture, huh?
Yeah. Right. So you can bring in the Lagrangian and you can maximize over alpha greater than or equal to 0, and you will end up with the same problem. Right? If the constraints are satisfied, then this whole thing will be f of minimizing f of w. If not, it will be infinity, right? I'm just repeating what is there in the lectures. So you can turn this therefore into a min-max problem. Okay, this is a min-max problem. Now, if I swap this min and max, I get a max-min problem, and we call that the dual of this, right? We call this the primal problem, and we call this the dual. And under certain conditions, the primal and dual are going to return the same solution, and that configuration is called strong duality, right? So
when both of them are convex, then only it is strong duality.
Yeah, so in F and G are convex. In addition, we have some more conditions. They are some regularity conditions, and we are not mentioning that in this course. So in such conditions, you have what is called a strong duality. Now, this is the theory. Okay, now let's look at our problem, which is what we are concerned with where this is the function we are minimizing, right? So for us, it's norm w square by 2 subject to n inequality constraints. So I can now write this Lagrangian as this, right? So for each inequality constraint, I have one alpha I. And can someone tell me why I have written it down like this? Why is it 1 minus W transpose Xi YA?
Satisfy the constraint.
Right, but
It's in the form g of x less than or
Yes.
equal to 0, right?
correct.
Standardized, yeah.
Right. Okay, so that is why we have written it this way. Right? So this will be 1 minus W transpose Xy less than or equal to 0. Right. So that is what we have done here. And finally, the corresponding dual problem is you swap max and min, and you have this dual problem. Okay, so from the point of view of both the exam and later on, if you don't want to get into the math too much, it's enough if you understand that there is something called the primal problem. You can build a dual problem corresponding to that, and when the functions and the inequalities are convex and certain other conditions hold, solving the primal problem and dual problem amounts to the same thing. And in some cases, this dual problem, solving it might be easier than solving the primal problem. Okay, this is the theory that you need to know roughly.
But sir, graded assignments and all are filled with mathematical problems.
Okay, yeah, they wouldn't ask you to prove or go into.
No, that kind of proof is not there. Yeah, I know proof is not there. Anyhow, on Monday we'll discuss the mathematical problem.
Yeah. So now this dual problem is there with us, so we have to solve this. So can someone tell me what you understood from the lectures? What happened here? what is this arrow that I've drawn here, and what is this?
So the one in the box is an unconstrained optimization problem,
Okay.
and the W, it's the solution of it. W equals sum over I. That's the solution of it.
Okay, that is correct, right? So one advantage of writing it in this dual form is that as you said, the box, whatever is inside the box, it's unconstrained. So you just take the gradient of this expression, the Lagrange. Basically, this is the Lagrangian, right? This is the Lagrangian. You take the gradient and set it to 0. You will end up with W as sigma alpha I xioa. So what you need to understand from all this is that W is a linear combination of your data points. Now, where else have we seen this configuration arise?
In linear regression,
In linear regression, is that the only place, or you have seen this somewhere else?
even before in PCA, I
Isn't
think we have.
the same? It's the basically it's some loss plus regularizer, all the same structure. Is that what you're looking for?
No, like the question I'm asking is, what? Why is where else have we seen this W being a linear combination of the data points?
Wherever there's a kernelization, there is.
Not really, right? I mean, we are not yet kernelized it, so
I know, but okay. Is it that the case in PCA and all of it? PCA also.
We have seen in regression also, sir. Like
so yeah, regression is one thing, as Sarvesh mentioned. Now,
yes.
is there anywhere else in the lectures has Sar mentioned this anywhere else?
feature with
Okay, so do you remember something called representative theorem that was mentioned in week 9?
Ah, yeah. Correct.
Right.
Sorry, sir, could you repeat that?
So in week 9, while discussing logistic regression, Sar mentions this part that your W can be written as a linear combination of the data points, even for logistic regression.
Right, sir.
Okay, so we are not going into that because that was not, I mean, that anyway, we are not covering that as a part of the course, and I also don't know what this representative theorem exactly is. So, but Sar mentions that W is a linear combination of data points. So we have seen this in regression. We have seen this in logistic regression. We are now seeing it in SVM also. Okay, it's a repeating theme, a recurring theme. All right. So any questions at this stage? How we got this, or okay? So the main thing you have to take away is that W can be expressed as the sum over data points, and alpha I is the importance given to each data point. Okay, that's the main takeaway. So now if you plug this W back into this, you can now plug this W back into this, and you can express the optimization problem in terms of alpha, right? So in order to do that, we are going to write W as a product of some matrix terms and some vector terms.
Can I ask? Maybe this is. We should have probably asked this in the MLF stage only. But when we take this Lagrangian, right? Why do we maximize alpha? Why do we want to maximize alpha? That's something which I'm not very clear about.
So that is because of that's the definition of dual problem, right? By definition, when you flip the min and max, you get the dual problem.
Correct. I'm saying even before that, even before flipping min max, see, this is clear. We had to minimize FW, and we take GW alpha. Why are we obliged to maximize alpha in this Lagrangian?
So as to make it equivalent to the primal problem, right? It's just a different. So see, we want to somehow bring in this min max maximum, right? So one way of is just a way of rewriting the primal in terms of some other optimization problem.
Basu, I think yesterday sir has shared, some links of MLF sessions again, right? So I was just going through them. So I think in the definition itself, professor has clarified it somewhere. The way it has been defined. So there are two conditions. Whether once it will be infinity, and the first time it will be fx. So that is possible only when alpha is greater than equal to 0. So I think it is as per definition. That's my limited understanding. If required, you can watch those videos again.
No, I will watch it
All put
because it's
together,
some.
all put together is 1.5 hours. So you can watch it again. There,
Yeah, no, I'll watch it. It's a good idea actually.
yes.
In some places, they don't take this GW as, they don't take it as 1 minus. They leave it as such, and they take FW minus alpha into GW.
Yeah, that is again for the same reason, right? There the constraint would be g of w greater than or equal to 0. Then you
Yeah.
have to take alpha less than 0, less than or equal to 0. I mean, sorry, if alpha is still greater than or equal to 0, then you'll have to do f of
Yeah,
w
actually, that
minus.
is, yeah. So if this is negative, that means we are trying to increase, basically minimizing FW is like maximizing the right part of this term, right?
Minimizing.
Minimizing FW is the same as in this Lagrangian, it's same as maximizing alpha into GW, right? Because okay, got it now. I got it. I got it. I got
Okay.
it. I got it. I got it. Sorry. Thank you.
Yeah. So right. So for our course, let's take g of w less than or equal to 0 and alpha is greater than or equal to 0, right? So it is plus, right? So now, yeah, does everyone understand what was done here? Xy alpha. How we arrived at xy alpha? Is there anyone who didn't understand this part?
Alpha, we can flip from the left to the right, is it? It's not going to be an issue. Like above W is written as sum of alpha xy.
Okay. So see here, alpha I and yi are scalars.
Okay. Okay.
Okay, so alpha I and yi are scalars, and xi is the only vector. Now, what we are doing is we are now putting all these n alphas into one vector, and alpha has to come here, right? So this is a matrix vector multiplication. So xy is this matrix, and we are multiplying it with the vector alpha. So this will become what? The linear combination of all these n columns, and the weight is alpha I. Is that clear, or this is still a bit unclear? If you want, we can go over this, but
No, actually, I kind of took x as something, y as something, alpha. I actually multiplied and refactored, and I get this.
okay. So if you want, we can go into this. If not, I'll just leave it and go.
See,
Right?
Can we?
Yeah, I don't mind. So I just yeah. So let's
it'll work out. It'll eventually work out.
yeah. So that is see this is a thing that I think we should do early on, because this matrix vector multiplication is probably like we don't matrix multiplication, we teach it in a certain way, but so let's take the concrete example of just 3 data points. I'm not going to give numbers here, but I'll just make this 3 data points so that have x1, x2, and e, and you have corresponding to this y, this y1 0 0. Okay, so this is x for 3 data points. This is y, and this is alpha. Alpha is going to be vector of size 3 again, right? So alpha 1, alpha 2, alpha 3. This is so far so good, right? Is there any confusion so far?
It's clear.
Okay, so these are 3 data points, and we have this. Now, where do we start? So xy is probably easier to compute. Now, I need to know if you all agree with this. If I say x into y. Okay, so do you agree? Will you agree if I tell you that x into y is actually equal to
The first feature of x1 and 2y1.
Actually equal to this thing, x into the first column of first. How do I write this? Give me a minute. So call this f1, right? For want of a better term, you all agree that x into y is nothing but x into first column of y, x into second column of y, and x into third column of. Is that something you are aware of?
Yes.
Okay, so now what is x into first column of y?
Okay. Can I ask a question here before we go further? X1 constitutes F1, F2, F3, right?
No, not F1, F2, F3, but F1, F2, so on till Fd, right? Assuming there are D.
Right. In this case, the way okay, understood. F1 to Fd. So X1, first feature of X1 into Y1 is what we are representing by XY for alpha 1.
First data point into I1 is what we are representing by XY.
But rest of the features are okay. First feature, okay. First feature of X1, no. First feature of all the X into Y basically is the first feature of X1, Y1, because rest of them are zeros on the Y side.
On
the Y.
Yeah, so let me just let's do this part first. I think this will be a bit easier. So I'll show you this. Sometimes, yeah, I think numbers should help here. This is what I'm trying to say. So when you multiply a matrix, right? Now each column is a data point, right? Each column is a data point. Now,
yes.
So let's do matrix vector multiplication, right? So let's say I have a vector that is B, right? So it's a very important operation that we all need to be aware of. If I multiply AB, what do I get?
Okay. 3 by 1 vector.
First column.
3 by 1
Yeah.
vector.
Right. So yeah, see, this is what you have to understand, right? You should not be multiplying it the traditional way, which is 1 2 3 1 0 0 4 5 6. Yeah, that's correct, right? That's the way we have been taught matrix multiplication. But here, that's not what you have to apply. What you have to apply is when you multiply A with B, that's like this. You'll get the first column of A. Of course, you can do it and see. You'll do 1 2 3 1 0 0. You'll end up with 1. You'll end up with 4. You'll end up with 7.
So we'll get the same answer even if we do like that also, traditional matrix multiplication.
Traditional, yeah, but this, see, that the problem, how do I put it? See, there is a problem when you look at it that way. When you multiply, this has, how do I put it? This has lot of links with linear algebra. So, okay, what about 1 0 1 0? What will you get? You should not think so much. You'll get the second column, right?
Okay, yes.
Right. So that's why I'm saying don't think about matrix vector multiplication as multiplying it in the traditional sense.
Even though we get the same result.
Yeah, even though you get the same result, right? You are right. Both are the same. But you will get, if you multiply this, you will get the second column. So what will happen in this case?
Third column going by that.
Third column, right? Of course, you can verify 1 2 3 3 will remain, and then 4 5 6 6 will remain, 7 8 9 9 will remain. So in general, it turns out you can do this. If you multiply this by x, y, z, what do you get?
First column
write
into
B
X
as a linear.
Go on.
Yes. So we could write B as a linear combination of x times 1 0 0 plus y times 0 1 0 and z times 0 0 1, and then multiply and use those previous results which we
Yeah, that's very good, right? That's a very nice way of putting it because that clarifies everything. So we all agree to what Sarvesh mentioned just now.
Yep.
Yes, yes, yes.
Right now, you can do this since you can write B this way. A into B is now what? A into B is what? You already know what A into 100 is, right? First column. So X is just a scalar. So it becomes X into the first column of A,
Hmm.
right?
147.
And plus Y into the second column of A is 258 plus Z into third column of A. Okay, so whenever you see matrix vector multiplication, it's almost always better to think of it as a linear combination of the columns where the coefficients are nothing but the elements of the vector x, y, and z. Is that clear now?
Yep.
Okay, now when you think of vector multiplication, matrix multiplication, what you can do is uh, you can actually extend this and say that. So let me call this. Let A remain the same. Let A remain the same. Now, instead of B, you introduce what? Let's say you introduce.
Let us reverse it. 321654987.
So I let's I'm doing it this way, right?
Yeah,
Now,
yeah, yeah, yeah. No problem.
yeah, right now. What is AB? You know how to do it for one vector. Now, if I put one more column here, what is AB going to be? So, do you all agree that it's going to be A into this first column? I'm calling this F1 or C1, let's say for column 1, and A into second column.
X plus A into 147, would that not be okay?
Okay, so let's whatever like what Sarvesh mentioned, right? I'm going to write.
Yeah,
I'm going to split it in the following form as x into uh, x y z and sorry, not x.
147.
So I'm going to write this as x y z plus 000 plus 000 and ABC. Can I do this?
Yeah.
Okay, now if you multiply A with this matrix, essentially it will be a bunch of zeros here. So it's as good as multiplying A with the first column and having zeros in this place.
Yeah.
And A with and likewise here it will be A into the second column and zeros in this. So if you add them together, you will get A into the first column of B, A into the second column of B. Did everyone get this part? What we tried to do?
Yeah, but we sum it up, isn't it, in the end?
Yeah.
Yeah.
We sum it up, but in the process of summing it up, so this will be what? It will be AC1, comma 0 column plus 0
Yeah.
column plus AC2, right?
Yeah.
AC2. Okay, now if you understood this far, then you can now understand x y alpha, right? In two steps. You first do x into y, right? So x into y is what? The x into the first column of y. I'm calling it C1, x into the second column of y, x into the third column of y. Now, what is x into C1? A linear
What?
combination of what?
Y1,
Y1,
Y1
Sure.
into X1. Yeah.
correct, right? Y1 into x1. That will be the first column of x. This will be y2, x2, and this will be y3, x3. These will be the three columns of xy. Oh, if you multiply this with alpha, xy alpha, that is what? Again, matrix. This is a matrix and this is a vector. So it's a linear combination of the columns of the matrix with. So you will end up getting y1 alpha 1 x1 plus y2 alpha 2 x2 plus y3 alpha 3 x. Okay, this is what we wanted, right? So we wanted to write sigma xi alpha a xi yi in terms of these three matrix products. You get xy alpha. Is this marginally better than what it was before?
Yeah.
Okay, so this is xy alpha. Now, if you plug this back into the Lagrangian, you will get this. And I'm not doing this now because that will take us totally away from what we are trying to do. But if you want, we can do it later on, right? But do you understand roughly what this is trying to say?
Sir, Karthik says, I did this actually.
Yeah.
I did this and I got this solution. But the problem is I'm not able to reconcile the dimensions.
Okay. Which dimensions of which collection of
the final one, alpha t minus. So alpha is n into 1. Alpha is n into 1. So if you just write down the dimensions, the right hand side half whatever that value versus alpha t, those dimensions are not matching. I don't know what mistake I'm doing. Algebraically, I solved it.
Okay, so maybe this dimension we can work it out here. So we have
that's the only doubt I have.
Okay, so we have alpha transpose 1 minus half into alpha transpose some matrix. I'm calling this matrix Q.
Alpha.
Right. So alpha transpose Q alpha, where this Q is actually equal to y transpose x transpose xy. Right. So it's y transpose x transpose xy. So this is, let's first calculate Q. Q is going to be n by n, right? And the reason is y is what, n by n. So y is going to be n by n. X is going to be by n, and X transpose is going to be n by d.
Yeah.
By d, and y transpose is going to be again n by n, right? So y transpose x transpose xy will have n by n eventually, right? So this will have n by n. Now alpha transpose 1, right? This is actually alpha transpose 1. So this will be a scalar.
See, alpha is n cross 1.
Alpha is 1 cross n, right? Alpha is n cross 1. Alpha transpose is 1 cross n.
Yeah, n cross 1 into n cross this. The right hand will become n cross 1 again, and this will become 1 cross 1. Acha, this is sigma. Okay, this is basically alpha transpose is alpha transpose 1 means the sum of the elements. Is
exactly, yeah, that's correct. So this is actually a sigma alpha I. So let's write that down also. This is actually sigma alpha I plus half into. There is a nice way. It is actually this you would have done in MLF. So this is Qij alpha I alpha j. So this is it's called a quadratic form, or just a quadratic function of alpha I alpha j. This is all it is actually. The loss function in terms of alpha 1 so on up to alpha n, right? You have n alphas. Is actually a scalar. So it's a scalar function of these n variables. In the first one, you sum it from 1 to n. The next one, what you do is you have a double summation, and it's actually running from 1 to n. I runs from 1 to n, j runs from 1 to n. Qij. Q is nothing but the symmetric matrix given by this.
Yeah.
So, and that's the right. So this is a what? This is a quadratic function of in Lagrangian multipliers, right? Okay, does anyone have a question in this form? Because the final form is important to know. How you arrived at it is perhaps not all that important.
So here the final this thing is maximizing alpha, right?
Right, right.
Right now, now there is no constraint on that, right? Alpha now alpha 1 plus alpha, that maximizing that, there is no constraint anywhere.
We are constraining it by making it be greater than or equal to 0, right? That's the constraint.
Okay. Okay.
So we finally want to maximize f of alpha, the vector alpha, are subject to alpha greater than or equal to 0. Alpha meaning the vector alpha. So every single alpha should be positive, or sorry, non-negative.
Okay.
So does anyone else have any questions regarding this? Why is it called a quadratic function, or what are we trying to do here? Okay, right. If not, I'll go back. So this is what we are trying to maximize, and so if you solve this problem, you will get some alpha star. Okay, so why are we doing all this? Because this dual has some advantages. So in the case where n is very small compared to d, your optimization problem is simpler, right? Because you are solving for a lesser number of variables. And the other thing is that unlike the primal problem where you had n difficult constraints, here your constraints are simple. All that we need is to alpha should be greater than or equal to 0, right? So these are just bounds and not some complex looking constraints. The final advantage is that you have kernels, right? X transpose X, you can always replace that with K of the kernel matrix, and that will help you kernelize the whole thing.
So can you go back to the that one slide you had written, that quadratic form, just for 1 minute?
Yeah.
You'll save this also, right, sir, for us?
Yeah.
Why is the n by n, is it?
Y is n by n, right? Diagonal. So it's a diagonal matrix whose
okay,
diagonal
on the
elements.
diagonal. Okay. Diagonal. Okay.
One second, sir.
Yeah.
Okay. Okay.
Okay. So yeah. So that is that, and now so this is the dual, right? So where are we? Now we are ready to talk about support vectors. It is more important than the previous ones from a more practical context, right? So yeah, so what will happen is if you plug in your data set into an SVM solver, that will give you the alpha star. Okay, we are not going to look into how to maximize this function. Okay, that is beyond the scope of our course. So all that we will care about is some oracle will maximize this expression for us, and that oracle will return alpha star. Okay, and once you have alpha star, you already know that W is a linear combination of alphas, so you are safe here. Right? So you can now recover your W star from your alpha star. Okay, so now all this we have done only to get the optimal weight vector W star. Okay, now here is what we do next. Okay, so once you have W star, you also have this complementary slackness condition, right? Which I hope you remember from MLF, or even otherwise Sarah has done it in the lectures. And this is the condition, right? So for every constraint, this alpha I star, the Lagrangian multiplier, multiplied with the constraint at that point should be 0. Okay, we know this from complementary slackness that this should hold. Now there are two conditions. Okay, let's look at one condition. Can someone tell me what this condition is telling us?
Means that alpha I should equal 0, alpha I star.
Okay, so what does this condition mean? The one leading to alpha I star equal to 0?
Um, yeah, so they are like beyond the boundaries, beyond the dotted lines.
Correct, right? So
No,
they
no.
are beyond the dotted lines, right? They don't lie on these two dotted lines. These are points which don't lie on two dotted lines, and since we are dealing with the linear separable case or the hard margin case, we are only this will only correspond to points that are beyond this margin. Okay, all these points which are surrounded by the small rectangle you see. So what happens in the case of W star transpose xi yi equal to 1? What can we say?
Those are basically on the line.
Okay, they are on the line. Okay, so in that case, what can we say about alpha I star?
You can just say that it's non-zero. That's all.
Correct, right? So it's non-negative, right? So you can say that it's non-negative. We still can't say if it will be exactly 0 or it will be strictly positive, right? So this is one way of viewing the support. We come to the support vector part, but this is one way of viewing this image.
Can you repeat this part? Okay, they are on the line. So
So this,
WT that automatically becomes, sorry, not automatically. Doesn't that compute to 0 or?
yeah, this
Who is
part
that?
becomes 0, right? The one inside the bracket becomes 0.
Yeah.
So I can't comment on alpha I star. I know that alpha I star will be non-negative from my constraints, right? So this doesn't give me anything new. Alpha I star is anyway greater than or equal to 0, whether it lies on the line or not. But if it doesn't lie on these lines, I can say certainly that alpha I star will be 0.
If it is not on the line, it is 0, is it? Is that
It
what you're
has to
saying?
be 0, right? Because if it is
Yeah.
not on the line, then alpha I star is forced to be 0. But if it is on the line, then all that I can say is that it is alpha I star is greater than or equal to 0.
So, sir, alpha is the impact. Like by alpha, we are measuring the impact that a particular point has, right?
Correct, yeah.
All
The
right.
impact it has, right? So now we look at it from the alpha I picture. If alpha I star is positive, strictly positive, then the point has to lie on the line. Okay, again be the same complementary slackness, right? If alpha I star is positive, the point corresponding to that is forced to lie on the supporting lines. Okay, but here is small catch. Every one of these points need not be having positive alpha I star. Okay, so this is like that's the only catch, but it's a very subtle catch. Usually, you will find that most of the cases it's positive, right? So we don't even need to
And
worry about.
it depends on where you start from. Do we start from primal or do we start from dual? If we start from dual, then we can certainly say that from here alpha star is greater than 0. That means the points lie on this thing. But if you start from the earlier condition, see, one way we can certainly say that it will lie on the, okay, so here is the thing. If it lies on the line, then alpha,
We can't comment on alpha I star, right? So if it doesn't lie on the line, we can for sure say that alpha I star is 0. If it lies on the line, we can't be sure. So that is one way of looking at it. The other way of looking at it is if alpha I star is positive, it surely doesn't. It surely lies on the line. Okay? If alpha I star is 0, then we can't say that. All that we can say is it either lies on the line or beyond the margin.
correct.
Right. So the same thing, whatever you have said, I have mentioned it here. So we define a support vector to be a point for which this alpha I star is positive, right? Because only they contribute to the W star. Okay, only they lend their support to building the weight vector. Every other alpha I star, which is 0, is of no used to us, right? So we are only interested in these points. And according to what
Can we say this? Okay, just see if this makes sense, sir.
Yeah.
So there are three there are two kinds of points which are support vectors, right? One is the ones which are within the margin or misclassified, either of them, right? That is one. Okay, I know you're not come to soft margin, but either they're misclassified or they're within the margin.
right?
The points on the line may or may not contribute, may or may not be support vectors.
Correct.
Okay.
Yeah.
Right, that's the not all the points on the line are support vectors,
Right.
but support vectors will definitely be on the line or inside the line.
Right. Okay, so and same thing I'll be writing down, but only for the hard margin case. So every support vector has to lie on one of these two lines, right? So every support vector alpha x star is greater than 0, right? So therefore this has to be 0. So it has to lie on the two supporting hyperplanes. No, there's no escaping this. Every point that is not on the supporting hyperplanes, that will have alpha x star as 0. Right? Everything that's beyond the margin and not on the two supporting lines will have alpha x star as 0. The only thing which we can't claim is this, right? Every point on the two supporting hyperplanes need not be a support vector. So do you all see the difference between these three statements? Slightly different statements. Does anyone have any questions regarding these statements?
But what happens to the ones which are within the margin, sir?
They will not come into the picture for hard margin, right? Because nothing will fall within the margin for hard margin SVMs.
Okay.
Okay, but you are right that I think Sarah has done that part in week 11. Is there anyone who's having a confusion about these three statements? So I just repeat this part. So every point for which alpha is greater than 0 is a support vector, right? So that is the definition that you should take home. Alpha greater than 0 are support vectors because they only support you in building the W star. Okay, if alpha is 0, then I don't really care about the data point and it's not useful to me. So alpha greater than 0, support vector. If a point is a support vector, it has to lie on these two lines. Okay, these two are perfectly true. Only thing which we can't say is that every green point that lies on this line or every red point that lies on this line, we can't call it a support vector. Okay, that's all we are saying.
It's like converse need not be true, basically.
Right. That is the main point.
What did you say, sir? We can't call them points on the line. What did you say, sir? Sorry,
every support vector will have to lie on the dotted lines.
Yes.
But every point on the dotted line need not be a support vector.
Okay.
So, sir, in essence, whatever we classify as a support vector, it must necessarily lie on one of the two hyperplanes.
On the supporting hyperplanes, yes.
All right, got it.
So can you show those three statements again?
Okay, is that fine? Shall we move on?
One second.
Yeah.
You're saying every support vector lies on one of the hyperplanes. Correct. Lies on the support plane, supporting hyperplane, right? Yeah, correct. One second.
Yeah.
Go ahead, sir.
Yeah. Okay, so that is support vector. Now is here the overall view of hard margin linearist. So we call it hard margin because there is a hard margin, right? I mean, nothing falls within the margin. It's like a perfectly linearly separable case. So in practice, this is the picture, right? The black box view of SVM. You are given a data set. Okay? You are given a data set, bunch of red points, bunch of green points. You pass it into a black box that you call the SVM solver. What that SVM solver is internally going to do is it's going to formulate the dual problem, solve for the dual variables alpha 1 to alpha n, okay, and it will spit out the alpha star. Okay, it will spit out the optimal dual values. Once you have the alpha star, you can construct the W star. Of course, the solver will also give you W star. You can assume that. So it will give you the W star and also the alpha star, right? So you know both alpha star and W star. And using that, you can construct your decision boundary. Now, when it comes to prediction, note that all that you need is W star. You want Y hat, you don't need to know anything about these dotted lines. You just need to know is W star transpose X non-negative or not. Okay, that's all you care about when it comes to prediction. But for training, of course, you need all these other things. Okay, is this black box view of SVM clear?
Oh.
Okay, so this is one thing. And now we come to soft margin. I can continue, or shall we continue with soft margin for a bit and stop? Or do you?
So we can continue a bit on the soft margin.
Okay. All right. So here is what happened. So far we have looked at the hard margin case, right? So everything lies beyond the margin, and we had
can I suggest something, sir? If everybody is okay with it, because we will have 2 more sessions for week 11, right?
Yeah.
Right. So one session maybe we take the entire soft margin case, because there is 1 week here and 1 week in week, or a couple of sessions on week 11, and then the third part is your boosting and bagging, right? That also is an option. We stop here and treat this one lecture as part of week 11, the whole soft margin.
We have a session on Monday also.
Yeah. So what I'll do is I have only.
Go ahead. But I just suggested that because a lot of soft margin actually comes in week 11.
Right. Yeah, you're right. So what I'll do is I'll just introduce soft margin and I'll tie this to week 12, because in week 12 we have a bit of SVM, not SVM, but Hinge loss, right? So I'll tie that here so that in case some of you plan to look at week 12, say today or tomorrow, that will be whatever I do now may be useful. Okay, so I just quickly finish in the next 20 minutes. I do that. So see, if the green point, right? Green point, remember, is +1, right? If the green point lies on the dotted line, is that a good thing or a bad thing? Are we fine?
It's a good thing.
It's a good thing, right? Because all we have wanted so far is the point should lie beyond the margin. So it's a good thing. So we don't need to do anything to disturb this green point. So I don't need to push it away, right? So I don't need to expend any effort in moving it away from my decision boundary, right? So in some sense, this is called, there's a variable psi I associated with each point, and it will become clear what it exactly means. Here, the psi A is going to be 0. Okay, so Sir calls this the bribe. How much bribe you have to pay so that this point is not correctly classified, so that it lies on the right side of the margin. Okay, so maybe if I do one more case, it might become clear what we are doing. Now, what do you think will be the psi A for this?
Also be 0.
This will also be 0, right? Did everyone get why this should be 0?
Correctly classified.
No, sir.
It's already on the right, like on the right side of wherever it should be.
Yeah, so
correct side of wherever it should be.
Right. It's we want this to be beyond this margin, right? So either on.
So it's already there. So we don't have to make any changes to it to get it to the correct side. It's already where it needs to be. Is
Correct.
that it?
Yes, exactly.
All right, got it.
Right? So it's already in the right position, so we don't need to do anything. Now here comes the first of the violations, right? So we call this case, remember, we use this word margin and this dotted line interchangeably, right? So it's like everything we end up calling the margin, but this is called a margin violation because ideally it should be either on the dotted line or away from it, but it happens to be between the decision boundary and the margin or one side of the margin. This is a margin violation. Okay. Now, how much bribe should I pay for this green point so that it goes to the right side of the margin?
Point 0.5.
0.5, right? That is correct. So you can now treat this as a distance, right? This line is at a distance of 0.5 from the dash, the solid line, and it's at a distance of 1. This dotted line is at a distance of 1. So if I push this by 0.5 towards the correct side, if I push this towards the correct side by 0.5, I'll end up making this point go beyond the margin. That's what I want, right? So psi a is equal to 0.5 for this one. Did everyone get this? Why?
Sir, here W transpose X equal to 0.5 initially, right? Hello?
So this point happens to lie on this line W transpose X equal to 0.5.
And the distance between that point and the decision boundary is 0.5, you mean to say?
Here we are looking at not the distance of this point from the decision boundary, but on the right side of the margin, this dotted line. See, our aim is what? Our aim is to move these margin violators to the right side of the margin, right? So they are violating the law. You want to push them onto the right side of the law, right? So your interest is this. I want the green point to be here. So how much distance should I move this so that it ends up on this line?
But that's matching, sir. What service is saying that green point is a distance of 0.5. So that's matching in this case because W transpose X is 0.5. So that point is a distance of 0.5 from the origin, and now we have to make it to greater than equal to 1, right? On the right hand side.
Right. Now the next example it won't match, right? So we come back.
Yeah.
See, if maybe the next example will be clear. Now here, what do you think psi a will be?
Going by previous logic, I will say 1. I may be wrong, but I will say 1.
1, right? That's correct because this point is currently classified. So I mean, not classified. It's at a distance of 1 unit away from where I want it to be. So I have to push it by 1.
Yes.
Sir, here I have a doubt. 1. So this is only true when norm of W is 1, right? The distance between decision boundary and the dotted line is 1.
Correct. Yeah. So
but norm is not 1 here.
So I'm loosely calling it a distance, right? Actually, it's scale distance. It should be scale distance. So if you want to call it distance, it should be 1 by norm W, the distance between these two lines.
Okay, fine.
Right, you are correct.
So actual distance is 1 by norm W, but we are just rescaling it to equal to 1.
Yeah, right.
Okay, fine.
Okay, now next case, what will be the, how much should I push this so that it falls on the right side of the boundary?
1.5.
1.5, right? So this is actually, if you notice, W transpose, this will be actually 1 minus W transpose X for this point, and it's 1 minus 0.5, and it will be 1.5. Okay, one more example. This is, I know it should have become clear.
2.
We have to push it by 2, and even further, we have to push it by, let's say, 2.5. So there is actually a nice way to compute psi a. Psi a is actually, in a general case, right? I'm drawing in the general case here. Psi a is equal to 1 minus W transpose Xi into Yi. Okay, or it could even be 0. So we express it as the maximum of 1 minus W transpose Xi Yi, comma 0. Okay, so you get this part, why I am writing psi a like this, or why we are allowed to write it like this.
Because if it's greater than, it's anyways beyond the margin, right? If it's greater than 1.
Correct. That's correct. That's the logic, right? If it is greater than 1, if W transpose X Y is greater than 1, it's on the right side of the margin, so you don't need to do anything. So psi a will be 0. If it is on the wrong side of the margin, then the actual line is 1, where we want it to go is 1, but psi a is w transpose xi yi away from it, right? So you have to subtract this 1 minus w transpose xi yi. That is the amount by which you have to push it. So it's the max of these two. That's what we have.
That is the minimum of psi.
Yeah, that's the minimum
You
amount
can
of. Yeah,
push
that's
it.
correct.
Yeah.
Correct. This is the minimum amount by which you have to push. Yeah, that's why we have the equal to. Otherwise, as you said, it should be greater than or equal to.
It
But
is greater than or equal to. Correct.
yeah. Okay, now if we plug this in, there is a cost associated with each data point. So if you add all these bribes together and push it into the objective function, you end up with this optimization problem. Okay, so interestingly, there's a way of rewriting it as follows. So we have just seen psi a is what? Max of 0, 1 minus w transpose xay. So can turn this into a unconstrained optimization problem like this. Okay, so this is called the Hinge loss formulation of SVM, because this thing here, max of whatever you see here, it's called the Hinge loss. You will see this Hinge loss in week 12, so you don't need to worry if you don't understand it now. In week 12 lectures, sir will discuss the Hinge loss, but since it's connected to SVMs, I'm discussing it now.
Sir, for some cases, psi I could be greater than 1, right? Like 2 or something.
Yeah, it's like, for example, this particular case, right? So if it's like a very bad violation of the margin, it can be 2.53.
Then, sir, how it is calculated like 1 minus w transpose xi yi? It should be w transpose xi yi is the positive quantity, right? And if it is
it will become negative, right? So when you are, this is w, right? W is pointing in this direction. So if it's a green point, yi is equal to 1. So w transpose x will be negative. No? So 1 minus 1.5.
okay.
Okay,
But
so for the
but also the yi is positive there. That's why it will be here. Yeah.
correct, yeah. So the psi a should be understood like this. For any given data point, how much should I move it so that it is on the right side of the margin? So if it had been a red point, I don't, for this psi a will be 0, right? If I change this label from green to red, psi a for this will be 0. So for red data points, you'll have to look at this line. How much should I push it so that it is on this side of the margin? Okay, so did everyone get this? Even if you didn't at this stage, it's not a problem, because we'll revisit this in week 12.
I have a question. Perhaps it's not. It's more fundamental. I'm just trying to understand here.
Yeah.
Of course, the math is something which I have to read about. But when you're pushing a data point, actually, I have some data. Let's say I have a point, and then I'm actually pushing it. That means I am altering the original data. Is that the way it can be interpreted?
No. So we are not literally pushing it. Figuratively, I'm saying that if you were to push it, by how much should you push it? Right. So we are not actually pushing it. So we are not changing the data at all.
Okay.
Right. So if I were, for example, this point is at a distance of 2 units from the place where I want it to be. I want green to be here. Correct. Now, if I want green to be here, the if is important. If green should be here, by how much should I move it? I must move it by 2 units.
Right.
Right. But you are actually not moving it. Right. So it is still
and
here.
W changes, or how is that in reality?
So in reality, the W is what you're optimizing for, right?
Correct.
So that will change. Now it will change in such a way that this whole expression now gets maximized. See, you're no longer only interested in maximizing the margin. You're also worried about how much bribe or how much cost you will incur if points do not fall on the right side of the margin. See, this is a cost associated with the data. So I'll just come to that. Maybe if I explain what these terms are, it might become clear.
Okay.
Okay, so can for those who have looked at, we all looked at week 6, week 7, and all that. So what does this look like? Does this look familiar? The expression here. Is this
Correct, sir. This is like loss plus regularizer, right?
exactly right? Exactly. So this is regularization, and this is your loss, right? This, in this case, it's called the Hinge loss, and it's very important to understand this. So note that the regularization is a function of the model that you're training, right? Like in linear regression, if you remember, in Ridge regression, what did we do? We had a loss term plus lambda norm w square, right? So the regularization part is a function of the model, okay? And there is a loss part which is a function of the data. So we have a part that is model dependent, which is what we call the regularizer. We have a part which is data dependent, which is what we call the loss. Okay, so you can view soft margin SVM as minimizing a loss function, which we call the hinge loss, subject to some regularization.
Oh.
Okay, now going back to Ravi's question, this, see, what we are optimizing is W. Okay, so we are trying to minimize the margin. So there are, sorry, maximize the margin. So that is still there. Only thing is that in the process of trying to maximize the margin, we'll suffer some loss, right? And we care about that loss also. So I have some pictures. I don't know if it will be immediately clear, but
Can we see it this way?
yeah,
At hard margin, there is no loss there, right? We either classify everything correctly or we don't classify.
correct. Yeah,
Here, we are looking for a margin. The higher the margin, the better it is, because you can be that much more confident about the prediction. Correct.
right.
So, whereas when we do that, there will be some points which will be either on the other side, wrong side. Something will get misclassified.
Correct. Yeah.
Essentially, here we are maximizing the margin, at the same time trying to minimize that misclassification, like
Exactly.
it
Yeah.
is with Rich or anything.
Exactly. That's exactly what we are trying to do. Right. So there are two terms, and these two work against each other, unfortunately, but that's the way it is, right? So norm W square controls the width of the margin. Smaller the value of norm W, wider the margin. Right. And as you said, wider the margin, larger the loss. Right? Because if you keep making the margin wider, and wider, you are going to end up violating the margin on several data points. Right? That is what the hinge loss controls. It controls the loss. So you have a trade-off. So you can't simply keep decreasing W because your hinge loss will go up. So you need a trade-off. That's the trade-off is controlled by this parameter C, right? So smaller the value of C, wider the margins. Okay, so again, there's another slide. I know it's too dense, but maybe this is better discussed once you are also done with soft margin SVM. But in case you're interested, I'll leave this with you, right? So smaller the value of C, wider the margin, right? So it's okay if many points are violating the margin. If C is small, it's okay if margins are violated. On the other hand, if as you keep increasing C, what happens? You are not okay with many points violating the margin. So you end up pushing for smaller and smaller margins.
Oh.
Okay, and in the limit C tending to infinity, this are mentions in Big 10 itself. We do not tolerate any deviation, right? So we do not want any points violating the margin. Therefore, that will collapse into the hard margin case.
Oh.
Okay. So
One question. Sorry. Go ahead. Somebody else.
yeah, so that's all I had. This is the last slide. So this is some terminology we'll use both in exams and in general. So you have to know this. So when we say SVM, we'll mention one of these four cases, right? It's either a the week 10 case is the hard margin linear SVM, right? And if you apply a kernel, we call it hard margin kernel SVM. And in week 11, we'll discuss soft margin linear SVM. If you apply a kernel, you will call it soft margin kernel SVM. Okay, so that's all I had.
Today we have not covered kernel parts.
Kernel, that's mostly we won't cover more than this. It will be like
Okay.
We may, but I should come up with an example. What we'll do on Monday is we'll take up a hard margin linear SVM case, try to understand how it works.
Just trying to recollect, I think Professor introduced the concept of kernel when there was, outliers, like points were not linearly separable, and
Out,
there were some
Not when
outliers.
outliers. Not
Outlier
when
means
outliers.
no outlier means there were some red point in the green zone and green point
Yes,
in the
yes.
red zone.
He was asking if there is a solution for the outliers, and then he highlighted that kernelization can be used, but it is not the optimal solution.
Yes,
It is at this point at which he introduces soft margins. I believe the outliers are
yes,
discussed at the end of the linear SVM.
correct. Even I recollect this. Yes, this is the case. When
correct,
he talked about outliers, and outlier means he said that when the red points are there in green zone and green points are there in red zones.
right. That necessitates the soft margin, but the kernel SVM will come in when structurally your data is having non-linearity, right? When it can actually be separated, but not linearly. It can be separated by some nonlinear curve, and then we start doing kernel hard margin kernel SVM. If it also has outliers in addition to structural nonlinearity, then you do soft margin kernel SVM.
Yeah. So
Right.
one question, if you go back to that reformulation of, in terms of Hinge laws, I'm just wondering because see here W is actually inversely proportional to the margin, right? So it's a little confusing, although W feels like it is the margin itself, but it's inversely proportional to the margin.
Right, right, yeah, yeah.
Is there a way of writing this in terms of gamma?
In terms of gamma, so this will be 1 by
That will be 2 by gamma, but what about W transpose X? That's what is the problem.
yeah, that is
Because
so you
gamma
can
is a scalar.
correct, yeah, that will be hard, yeah.
So
But here we are setting gamma to equal to 1, right?
And then only we come up with 1 by norm W and 2 by
but
norm
gamma
W.
is 1 by norm W, right? So
No, we are like in the lecture, sir said that we set gamma equal to 1 and W gets scaled accordingly, right?
yeah. So true gamma is equal to 1 because W is scaled. Otherwise,
Yes, that's one way
yeah,
of putting
correct,
it.
correct.
Yeah.
Otherwise, it's 1 by W. I'm saying norm W. Is there a way to? No, I'm just thinking if we write it in terms of gamma, maybe it will be more intuitive. But if it was possible somewhere or some place, it would have been already written.
Right, right.
Sir, week 9 started with perceptron, right? And
Yeah.
then we moved to SVM, and I think week 11 and 12 are also related to SVM only, ensemble techniques and all those things, right? Backing, boosting, and
Right, right.
I don't, yeah, so all these things. So all 4 weeks are related to perceptron, right?
All
All 4 weeks, 9, 10, 11, 12
Actually,
are
they are related to linear classifiers.
somehow interrelated, right?
Yeah, correct.
So whether perceptron also forms the basis for neural network, like you are also saying that in week 12 we will discuss a little bit about neural network. So whether
Yeah.
perceptron is the basis of neural network also, is it right to say?
See, there is this concept called multi-layer perceptron, which is like basically stacking several perceptron units in the form of a network, and then you can kind of call that a neural network.
Hmm.
So
But
in that sense, it is related.
yeah, he's right actually. See, I've watched all the 12 weeks, finished 12 weeks.
Very good.
12th week, the neural network bit is like 10 minutes here, very little, just basic introduction. Don't expect anything at all.
I know. I
Except
think
for
they will
some,
be covering in degree level in detail, right,
yeah,
sir?
Prof repeatedly mentioned that I'm just giving a very simple overview as to how this is an extension of, perceptron is actually a bit of a motivation for that. And it's just like think of multiple perceptrons stacked over each other, right? It's like that. And he said once you get to the deep learning course, you will understand all these things, how the weights are computed. It's far more complicated in terms of matrix multiplications and all that, right? So very limited, but what you said is absolutely right. Perceptron is a bit of a motivation for neural
For
networks.
the starting point. You can say.
Yeah.
Okay, so that's all we have for today.
I had a few questions. One, I wanted to check with you if you have come across any, like honestly, during MLF, while we did all of this and we probably also got good marks and all of it, intuitively I didn't understand the prime and dual as much as now. Slowly we are appreciating it a little more as to how it's being used. Have you come across any videos or anything where they show what is graphically happening? Like, let's say I take a function and I try to minimize it, but when I use a Lagrangian, how does that change? How does the primal change to a dual? How does dual make it easier? Like, have you come across any graphical videos, like graphical exposition of this concept? If there is something, please do share with us.
Okay, so that's what we will be doing on Monday. So what I'll do is I won't do the primal dual part, but for the primal dual part, you can follow this particular. See this. There is a course on convex on optimization. It's a great course. So I was watching this recently, and
Stephen Boyd one.
Not Stephen Boyd. This is from once Shirish from Professor Shirish from IASC. Right, there is one sequence of lectures which are outstanding, where
what is it called? Convex optimization.
It's called numerical optimization. So he discusses some examples here. For example,
point x bar.
Of course, these are not.
Chevade, ISC.
Yeah, these are not like proper examples in the sense that he uses a computer simulation or things like that. But his diagrams are beautiful. So
okay,
he gives.
Because I went through some of that material by Stephen Boyd. Even the like a rundown version of the main thing, even that was like difficult to comprehend.
Right. So this is a geometric. He has a specific lecture called geometric interpretation, where he says which is primal, which is dual, and so this is what happens and all that. But I would suggest these 41 lectures are like best, one of the best I've seen. Yeah,
I think Basu in NPTEL there are two more courses on optimization. One is offered by IIT Guwahati professor. So even I have not gone through all the lectures.
No, I'm planning. Actually, I missed this term, but I don't know whether I could have done it also. But I missed this term. I think the registrations will start in April or May for the next term, right? It happens twice in a year.
I was just searching by typing optimization, so a couple of courses came. So that much only I know. So you can explore that also. Yeah, the registration will start from April because the session starts from 1st of July.
Yeah, so I'm just wondering it is worth taking up one of these to understand.
Yeah, so that particular course you can look at that. He has gone into great detail and he has also explained it very well. Okay, so anything else? If not, we'll stop streaming anyway.